So I'm going to start the talk off by just sort of some sort of vague remarks about invariance and classification problems. So the setup basically is going to be that we've got some class of mathematical objects, and there's some kind of equivalence between them. So lots of examples of this. You can think of groups, and you're trying to classify them up to isomorphism. You can think of topological spaces. You're trying to classify them up to homeomorphism. Linear orders, you might try to classify. Of course, you could do it up to isomorphism, but you could also say, I want to do it up to biembeddability. And one of the major goals, basically throughout mathematics, is to classify objects. And a very good way to do this is to give complete invariance. So what's a complete invariant? Well, to each object in the class, so each little x, you're going to assign some invariant f of x. And the idea is that the invariant should tell you when two objects are equivalent. So the most basic form of this is that x and y are equivalent if and only if they get given the same invariant. So maybe an example from beginning of undergrad is that you can classify vector spaces by their dimension. Right? So to each vector space, you associate a number, its dimension, or I guess a cardinal, its dimension. And two vector spaces are isomorphic if and only if they have the same dimension. So the idea is you now know what all the different vector spaces are. But invariants are not always numbers. So for example, you can do homology or cohomology. You can get groups as invariants. You can get some other kinds of structures. We'll have an example in a second of some other kind of structure. And when you do that, you should not ask whether the groups are equal, but whether they're isomorphic. So there's also some kind of equivalence relation on the space of invariants. So you're classifying whether the objects are equivalent by assigning invariants, and then the invariants, whether the invariants are equivalent, should tell you whether the original objects are equivalent. So here's like a sort of relatively simple example where you're not just using equality on the invariants, but there's some kind of equivalence because you have to make some kind of choice in assigning the invariants. So we're going to look at what are called rank 1 torsion-free abelian groups, or maybe more simply known as just subgroups of the additive group of the rationals. So the way you should think of these is you take the integers, because you're always going to have the integers. Maybe I should say non-trivial subgroups of the rationals. So you'll have the integers. And then there's also going to be certain other integers that are inverted. So maybe you say, I want to add in a half. So you add in a half, which means you also add in 3/2 and 5/2 and so on. Maybe you want to add in all of the divisibilities by 2 to get the dyadic rationals. So basically, you're taking the integers and you're adding in certain divisibilities. So there's some pretty old invariants from the 1930s. The idea is you're going to take some element from the group A and some prime P, and you're going to look at what's called the P height of A. So you're going to say, what's the highest power of P that divides A? This could be infinity. So if you take the dyadic rationals, so you have a half and a quarter and an eighth and so on, then the 2 height of 1 is going to be infinity because you can divide 1 by 2 infinitely many times in that group. If you take, so for example, in the integers, you take the number 6, then the 3 height will be 1 and the 2 height will be 1, but all the other heights will be 0 because you can divide it by 2 once and by 3 once and by no other prime. In the rationals, everything is going to have height infinity because you can divide everything by every prime as many times as you want. And then, so you think of this for all the primes and you go what's called the height sequence. So you have this element and you say, how many times can I divide it by 2? How many times can I divide it by 3, by 5, and so on? And you're going to get this sequence of numbers. So you've got this height sequence. And we're going to say that 2 height sequences are equivalent if they're essentially finitely different from each other. So they should be infinity in exactly the same places, but otherwise you're allowed to change finitely many places. So we'll have some examples on the next slide. But the point is that all of the elements of the group have equivalent height sequences. So they might not have exactly the same height sequences in the integers. There's different divisibilities of 2 as there are of 6, but they're going to have equivalent height sequences. And we're going to call this equivalence class the type of the group. And it's going to be a complete invariant. So let's look at some examples. So the idea is we're going to take some group and we're going to pick some element, and then we're looking at the type sequence for that particular element. So if I take the integers and I pick 1, well, it's not divisible by any primes. So its type is going to be just the sequence of all zeros. On the other hand, I didn't have to pick 1. I could have picked any other element. So maybe I picked 12. So how many times is divisible by 2? Well, twice. And then it's divisible by 3 one time. And then it's not divisible by anything else. So its type sequence is 2, 1, and then a whole bunch of zeros. I could also take some other groups. So this is the integers, but I've added in a half. So I'm going to get 3 halves and 5 halves and so on, but I won't get a quarter in this group. And if I look at 1, now I could divide 1 by 2, because 1 divided by 2 is going to be a half, and that's in the group. But I can't divide it by 2 a second time. So my type sequence is going to be 1, 0, 0, 0, and so on. So these groups are all isomorphic. Obviously, Z is isomorphic to Z, but the point is that the type sequences are equivalent. Right? If I make finitely many changes to each type sequence, I can get each of these other type sequences. So let's look at some groups that are not isomorphic. So I could take the integers and I could invert all the primes. Right? I'm adding in 1 over p, but I'm not adding in 1 over p squared. And if I pick 1, then it's going to be divided by every individual prime exactly once. So my type sequence is going to be 1, 1, 1, 1 forever. So this is not equivalent to any of the previous type sequences because it's different on infinitely many places. Another group I could take is the dyadic rationals. So I'm inverting 2 infinitely many times. So now if I pick 1, it's divisible by 2 infinitely many times, but it's not divisible by any other prime. So its type sequence is going to be infinity and then all zeros. So these are not isomorphic to each other, and they're also not isomorphic to the integers. So this set, these type sequences are all equivalent, and they're inequivalent to these two, and those two are also inequivalent to each other. So for the third one, you see that the infinity is showing up, that even though these ones and this one are sort of equal at all but finite many places, that place is an infinity. And so they don't count as equivalent. That's like think of the infinity to finite as like an infinite difference. So the point here is that we're classifying these groups using these invariants, but we can't compare quality of invariants. These ones get different invariants, but we're comparing them up to equivalence of the invariants. So the picture now should be that you've got this X with an equivalence relation E that you want to classify. And a complete set of invariants for it is going to be some other equivalence relation, which is Y is the set of invariants, and F is the equivalence between invariants. And then you want this function that maps objects to their invariants so that 2 objects are equivalent if and only if their invariants, instead of being equal, are now equivalent to each other. Now, for invariants to be useful, you want 2 things to be true. One is you want it to be easy to compute the invariants. So given the object, you want to compute the invariant. The other thing is you want it to be easy to tell when 2 invariants are equivalent. So there's always sort of a silly invariant, which is you can use the structure itself as invariants for itself. So you can map a structure to itself, and you say it's isomorphic if and only if it's isomorphic. Obviously, you haven't actually done anything there. So on the right-hand side, the idea is that you want to say that there's a good classification if these things on the right-hand side are easier to compute somehow. So by easy to compute, what I'm going to mean is Borel. I'm going to talk about what Borel means in a second, but essentially you should think of Borel as being sort of reasonably constructible. So why am I saying Borel and not computable? One thing is that we're going to deal with countable structures, infinite structures. And some invariants that we're going to think of, we as mathematicians think of as easy, like the dimension of a vector space. You think, if I have a vector space, I can find its dimension. That computation is actually Borel and not just computable. The problem is if you're doing a computation in finite time, you can only really look at finitely much of the structure. And then, if you haven't looked at the whole vector space, how are you ever going to know what its dimension is? So Borel is some kind of generalization of a computation that lets us compute things that we intuitively think of as reasonably computable. Another reason is that if we want to show there's no good invariance, it's a lot stronger to show that there's no good Borel invariance rather than showing that there's no good computable invariance. So our like non-invariant results are much stronger in this case. And the last thing is, so if you're working with finite structures, then polynomial time is maybe the clear thing to use. And then you might say, okay, if I'm dealing with countable structures, what do I want to think of as the analogous thing? And there's reasons to say maybe it's not actually being computable. Maybe it's actually something like being Borel, or maybe just arithmetic. But essentially, you should think that what you might think of as a reasonable construction is probably Borel, and things that are not Borel, you might be things that you don't think of as a reasonable construction. So think of it as some kind of generalization of a computation that may not actually be computable, but is like reasonably describable. All right. So next I'm going to talk about what does Borel mean. And I want to point out that if you're not like too used to dealing with Polish spaces and things like that, you're not going to lose too much in the rest of the tutorial if you just sort of ignore the next section or follow as much as you can, but then just think of a Borel function as something reasonably constructive. So a lot of the rest of the tutorial is going to be actually constructing reductions. And so it's going to be an actual construction, and you can look at it and say, I see that this construction is reasonable. But for completeness, we're going to give some definitions of what it means to be Borel. So the mathematical objects we're working with, we're going to tend to think of them as coming from a Polish space. So a Polish space is a topological space. It's separable and completely metrizable. But maybe some examples: the natural numbers are a Polish space. The infinite binary strings, that's a Polish space. Or the infinite binary strings, the infinite strings of natural numbers, that's another Polish space. The one we'll be working with a lot is we're going to fix some language or signature L, and we're going to look at the space of all the different L structures. So we're going to call this mod L. So maybe first I should say, what do I mean by countable L structures? Really, you should think of mod L as structures as they might be presented as input to a computer. So their domain, we're going to take to be the natural numbers. So you could think of it really as picking some countable set of symbols for the domain. And so all the relations and functions of the structure are now going to be relations and functions on that particular domain. So the idea is we're not really thinking up to isomorphism. So we're separating out different isomorphism types, different ways of presenting the group on the natural numbers, and we're thinking of those as separate elements of mod L. So one structure is probably going to have many, many different copies inside of mod L, presented in different ways. So if you think of like the Cayley table of a group, the same group might have lots of different Cayley tables which look different. It's kind of the same thing, that you're presenting the structure in various different ways. And then mod L is a topological space, so I need to tell you what the open sets are. In this case, they're actually Clopen sets. Basically, what you're going to do is you're going to take some atomic or negated atomic fact about the structure. So if R is some relation, and if these are natural numbers, which we're thinking of as elements of the domain, then we can say, I'm going to take all the structures that have that true. So all the structures where this relation R really is true of these elements, that's going to be an open set, a basic open set. So then the open sets are going to correspond to saying, essentially, either this basic fact about the structure is true, or this one is true, or this one is true, or this one is true, and so on. So the open sets are basically sort of, you should think of it as like elementary facts about the structure. So the set of all the structures that satisfy some basic elementary fact. The continuous functions on mod L really are kind of analogous to computable functions. In fact, every computable function is going to be continuous, but not vice versa. So let me try to explain that. So let's think of a function from mod L to finite binary strings. So this function takes as input some L structure, and it's going to output an infinite binary string. So what's the topology on the binary strings? It's got the basic open sets that say, here's this finite binary string. What are all the binary strings that extend this? So the inverse images of those have to be open. And what that corresponds to is if you take some finite binary string sigma, you want to think of like how do I know for a structure whether it's going to output sigma when that structure is an input? Well, there's going to be some possibly countably infinite list of basic atomic facts about the structure, so that F applied to the structure is going to extend sigma, which means that you should think of it as like outputting a string extending sigma. The output is going to start with sigma, if and only if one of these facts is true about the structure. So you can kind of think that this is a computation. You're saying, what am I going to output? Well, I'm going to look at these atomic facts, and I'm going to check if any of them is true in A. And as soon as I see that one of these atomic facts is true in A, then I'm going to output some output beginning with sigma. So really it's saying you're looking at the structure, you're seeing what's going on in the structure, and there's certain things that you see about the structure that tell you what you're going to output. Now, why is it not vice versa? Well, the list of things that you're looking at, right, these lists of facts that you're looking for, those may not be computable. So, it's got this property of like being computable, that you look at the structure and you see what happens and you output something, but exactly how you're doing that might not be computable.
Rest of the output matter?
So then for each, for every sigma, this is true.
It extends the rest of the.
Yeah, so then you look at all the extensions of sigma, and they're each going to have a bunch of facts that say when they should happen, right? And so you can think that the output is living in the space of like all the possible binary strings, which is a tree. And you're thinking like for each next output, there's some facts that you're going to see that are going to make you output that.
So yes.
So really, yes, you should really think of it. It's really like a computation like that. Okay, so that's just continuous. So the Borel sets, you take the open sets and you take the closed sets, and you're allowed to take countable unions, countable intersections, and you're allowed to take complements. So you're building up these sets that are starting with these very basic sets, these atomic facts about the structures, and you're building up more and more complicated things. So intuitively, you should really think that the Borel sets are the ones that can be built by quantification over the elements of the space, but you're not allowed to use quantification over higher order things. They're kind of the most general sort of first order definable sets that you can get. So for example, in the space of infinite binary strings, if you look at the strings that have infinitely many zeros and infinitely many ones, this is going to be Borel. So it's not going to be open, it's not going to be closed. You can't, for example, if I give you an infinite binary string, you can't compute whether this is true or not, because you'll never have looked at the entire string. But I think you'd agree that this, it's a reasonable question to ask about a string. There's a reasonable, sense of how you would check if this is true about a string or not. So maybe take this as an example of why we want to talk about things that are Borel, but not just computable. So if you told a mathematician, I've got some decision procedure for deciding if these two things are the same, and at some point you have to decide if a binary string has infinitely many zeros and ones or not, I think most mathematicians would say, that's a very reasonable thing to involve in your procedure. Okay, so a function is going to be Borel if the inverse image of the open sets are Borel. So if you're continuous, that's the inverse image of open sets are open. So every continuous thing is Borel, but Borel things, you're just allowed something a little more complicated. If you think of this in terms of computations, what it's really saying is that when you're deciding what to output, you're not just looking at these basic facts about the structures, but you're looking at more complicated facts. So for example, you're allowed to ask, you could say, I want to output 1 if there's an element in the structure such that for every other element, something happens, and otherwise I'm going to output 0. Essentially, to decide how you're going to output things, you're allowed to ask a little more complicated questions, but still really first order quantifiers over the structure. So computable functions are continuous functions are Borel, but none of the reverse are true. So as I said, you're not going to lose too much if you just think of Borel functions as reasonable mathematical constructions in the rest of the talk. And a lot of the things we're going to talk about are just examples, and you can look at them. And in fact, a lot of the examples will actually be computable functions, but not quite all of them.
Really good examples of things, but they're not arithmetic.
Yeah, so even that I think is not there's not any great examples of that. Oh, yeah. So Rod asked, so an arithmetical thing is basically you can take, so what in the definition of Borel, you can take arbitrary intersections and unions, and you can do that sort of as many times as you want. Arithmetical is really saying you can only do that finitely many times. So you can only ask, there's finitely many quantifiers that you're asking about. And essentially all the examples will really be arithmetical. But there's this sort of sense in which, if you restrict arithmetical, there's going to be like weird edge cases. And so if you're sort of developing the theory, then Borel is just like smoothing everything out. All right. So what does this lead us to? Basically, this idea of a reduction between two equivalence relations. So you have equivalence relations E and F. So they're on Polish spaces. We're going to say that E is reducible to F, and we're going to write E is less than or equal to Borel F. Basically, if there's a function from X to Y, so that two things are equivalent in E, if and only if their images are equivalent by F. But here what's happening is this reduction is going to be a Borel function. So it's a reasonable construction of these invariants. So you should think like any reduction, this really means that the equivalence relation F is at least as complicated as E. Or another way to think of that, so maybe two ways to think of that. One is that if you had some way of knowing whether things are F equivalent, then now you can figure out if things are E equivalent. If you take being Borel to be a reasonable construction. Another way of thinking about it is if you had any Borel invariants for F, you could pull them back to get Borel invariants for E, right? So Borel invariants for F would essentially be another reduction happening over here, and then you could do the composition of the two and get invariants for E. So like every reduction, this is saying that one thing is simpler than the other. Okay, so in this talk, I mostly want to talk about isomorphism of countable structures. And isomorphism, if we look at the equivalence relation, that's not a Borel set. It's actually an analytic set. So to define if two things are isomorphic, in general, I need to use a second order quantifier. I need to ask, is there a function between them that acts as an isomorphism? So this is an analytic set. Essentially, here's the definition, but really it's saying you're using this existential second order quantifier to define the set. So in descriptive set theory, there's an entire field of studying equivalence relations up to Borel reducibility. A lot of what they do is when the equivalence relations are Borel. But in this tutorial, I'm really going to be focused on the specific problem of isomorphism among countable structures. And really, the focus is going to be on different kinds of structures. So on groups and fields and graphs and linear orders and how these all relate to each other. All right. So you sort of got the preliminaries out of the way. So now we can get to the main definitions. So there was a really seminal paper in 1989 called the Borel reducibility theory for classes of countable structures. So this is by Harvey, Friedman, and Stanley. And they said, okay, let's look at Borel reduction between classes of structures in the following sense. So suppose I have two classes of structures, possibly in different languages. So one could be some class of graphs, could be all graphs, it could be specific kinds of graphs. The other one could be, say, fields. These classes should be closed under isomorphism, so I'm really thinking of them as sets of isomorphism types. And we're going to say that K is Borel embeddable in K prime if the isomorphism on K is Borel reducible to isomorphism on K prime, right? So what that's really saying is that there's this Borel function phi, and it's taking a K structure to a K prime structure, so that if they're the original things are isomorphic, if and only if the new things you built were isomorphic. And so we're going to say that K Borel reduces to K prime. So the way you should think of this is maybe on the left-hand side, for K, you have graphs. On the right-hand side, you have groups. So given a graph, you want to construct a group, right? You want to give a general construction. So from any graph, you build a group so that the two graphs are isomorphic, if and only if the two groups are isomorphic. And again, you should think of this as saying that any invariants that you could use to classify K prime, you could pull them back to classify K. So this class of structures K prime is at least as hard to classify as K. So let's give a little example. So the class of Q vector spaces, which have this invariant of the dimension, it's Borel reducible to the class of subgroups of Q, which is this other example we saw, but not vice versa. So to do this, I'm going to take a list of the primes. And given a vector space, I need to tell you a subgroup of Q. So what am I going to do? I'm going to take the dimension of the vector space. And I'm going to take that prime. And I'm just going to add divisibilities of that prime as many times as I want. So maybe this is technical. Sorry, what I should really do here. So V is infinite dimensional, then this doesn't quite make sense. What I should really do is invert all the primes less than the dimension. So that's going to work. Right, and the idea basically is that I've encoded the dimension of V into this group, into the divisibility relation of that group. It's going to be a lot harder to show that there's no Borel reduction in the other way, but you can do that. So there's this theory of Borel equivalence relations, and for Q vector spaces, they're classified by what's called equality, equality of the dimension. For the subgroups of Q, it's a relation called E0, and you can prove that the one doesn't reduce to the other. So one of them is more complicated to classify than the other. It's kind of saying that, in classifying the subgroups of Q, we really had to have some non-trivial equivalence relation that we classified up to. So there are structures which are as complicated as possible for a structure to be. So we're going to say that class of structures is Borel complete if every other class in any language reduces to it. So in practice, when this happens, the Borel reduction is almost always a computable reduction. And we'll see examples of where that's true. So these structures, basically, the idea is isomorphism for these structures is as complicated as is possible for isomorphism to be for any kind of structure at all. A classical example is the class of all graphs is Borel complete. So I think there's maybe 5 different versions of saying something about graphs are as complicated as things could be. This is one version of saying that. So let's see why. Let's see the construction. So we want to do, right, what are we trying to do? We're trying to show that every class reduces to graphs. So we want to fix some language, L. For simplicity, just for the example, let's say that L has a binary function symbol. And what we want to do is we want to say, for every L structure A, we want to produce a graph so that the 2 original structures are isomorphic, if and only if the graphs we produce are isomorphic. And this should be, right, a reasonable construction, this phi. It'll actually be computable. And the idea is that the structure A is going to somehow be embedded into the graph that we construct. So what are we going to do? We've got this graph phi of A we want to produce. We're going to take the elements of A, and we're going to put them in directly as vertices. But the graph is going to have all sorts of other vertices. So we want to distinguish which vertices came from A from the ones that didn't. So we're going to pick some widget, some little graph, finite graph that we're going to attach to things. And we're going to use that to identify the vertices that came from A to distinguish them from all the other vertices. So for example, lots of choices you could do. One thing we could do is if we want to have this A, which is representing an element of the original structure, and we're going to attach a fork-leak to it. So when we look at the graph and we see, hey, here's an element, and it's got a fork-leak attached, we know that that element was really representing something from A. If we look at these other vertices, right, these are these other vertices that might show up in the graph. They don't have fork-leaks attached to them in the same way. So we know they don't represent elements of A. They're just extra elements that are coding things. And then I need to tell you something about how the function is going. So say I've got 3 elements of A, and f of A, B equals C. I want to represent that in the graph. So remember, A, B, and C, those are all vertices lying somewhere in the graph. What I'm going to do is I'm going to attach some other widget to them. So I'm going to take this pentagon with a line across, but there's tons of different widgets that you could use that would all work. And I'm going to attach the first thing to here, the second thing to here, and the third thing to here. And that's going to represent that f of the first 2 is equal to the third. So you should also remember that each of these vertices also has that previous widget attached, right? So there's a fork-leak attached to here, and attached to here. But we're not attaching those fork-leaks to these things. So that shows that there are these separate elements that are just used to code things in. The other thing that's important is when we look at the graph and we see a widget like this, we can tell which is the first element attached, which is the second, which is the third. Because you see this pentagon, you see the line across, and then this vertex, and this vertex all look distinct from each other. This is the one that's part of the 3 cycle, but not the 4 cycle. This is part of both. This one's the one that's part of the 4 cycle. So your widgets have to be like distinguishable, and neither of these widgets embeds in the other. So you don't accidentally see a fork leak that wasn't one that you put in there, or things like that. So you just have to be a little careful, but essentially any kind of generic widgets will work. And then the idea is that if you've got a copy of this graph, you can recover a copy of the original structure. So the first thing you do is you search for these vertices that had a fork leak that was marking them as really belonging to A. So you can pick out these special vertices from the graph. And then you want to recover what the function does. So for any 2 vertices A and B, you're going to look for some third vertex C. And these should all be these special vertices that were specially marked. And then you want to look for one of those pentagons with the line that they're all attached to. And they should all be attached in the right way. And once you find a C like that, then you say, I know that F of A and B is going to be equal to C. So you've encoded this original structure into the graph in a way that you can then recover it. So I think there's tons of different constructions you can do that'll work, but you just have to be a little careful that you make it work out, right? You have to choose the widgets properly, and then you're going to get an isomorphic copy of A back in a unique way. So this was just for the one function. Right? If there's more functions or relations, then you need to include more widgets that represent what's going on with those. If you have a relation, then often you'll want to add a widget to represent the negation. So if the things are related by the relation, you put one widget attached to them. If they're not related, then you put some other widget attached to them. And that lets you computably recover whether the relation held or not. So, but in general, this is really the idea, is you're coding things into the graph. All right, so this is the argument that the class of graphs is Borel complete. And this is generally the structure of how these kinds of arguments work, is that you take the one structure and you encode it somehow into the other structure. Now that you know that graphs are Borel complete, if you want to show that anything else is Borel complete, you can just reduce graphs to it, right? So for graphs, we have to reduce arbitrary L structures. But now that we know graphs are Borel complete, we can just say, I'm going to take a graph and turn it into a field or a group or whatever kind of structure we want. Okay, so one of the things that you want to think about sort of generally is that there are some analytical equivalence relations that are not isomorphism, other things that are not Borel reducible to isomorphism of graphs or of any countable structure. So just a couple examples. So there's like bi-embeddability of graphs or homeomorphism of compact topological spaces. These don't reduce to isomorphism. So when we say that something's Borel complete, what we really mean is that it's Borel complete for countable structures. So it's not as, the isomorphism is not as complicated as any equivalence relation could be. It's just as complicated as any isomorphism equivalence relation could be. And there's like particular things that go on with isomorphism equivalence relations. So for example, Scott's isomorphism theorem says that if you fix one particular structure, all of the other structures isomorphic to it, that's a Borel set. And what that means is that every equivalence class is actually Borel. So even though the equivalence relation as a whole is not easy to construct, each orbit is individually easy to construct in sort of a non-uniform way. So if I tell you the orbit, you can tell me how to construct that orbit, but you can't tell me construction of all the orbits at the same time. So this is like some special property of isomorphism equivalence relations that's not true of equivalence relations in general. Okay, so then you have the question of what other classes of structures are Borel complete. There's a whole bunch of examples in the original paper of Friedman and Stanley. I want to focus for the next little bit on these classes, but there's all sorts of other things that will fit in this list also. So these are all Borel complete. There's all some way of coding graphs into the given class. Sometimes you might do it a little indirectly. So in Maria's talk this morning, she wanted to code arithmetic into something. And instead of coding arithmetic in, she first passed to partial orders and then encoded the partial orders. So it might be that just because of whatever structure you're trying to code into, it might be easier not to code graphs, but to code something else. But I think the vast majority of cases, graphs are the easiest thing to code. So I'm going to give a little example just to show how these kinds of things work. We're going to show that partial orders are Borel complete. So the idea is we have a graph, and we want to turn it into a partial order. Again, the two graphs should be isomorphic if and only if the partial orders we produce are isomorphic. So the domain of the partial order, we're going to have two special elements, A and B. Then we're going to have all the vertices of the graph. And then we're going to have a new element, X, for each potential edge. So this is not for the actual edges, but just for every pair of vertices, we're going to have a new X. In the partial order, we're going to put A bigger than all of the vertices and B smaller than all the vertices. The idea there, that's kind of playing the role of this for clique we put on before. We want to distinguish which elements are really representing things from the graph versus things that are not. The V's are all going to be incomparable to each other. And then we want to code in the edge relation. So for each potential edge, if it really is an edge between U and V, then we're going to put this thing below the two vertices. And if it's not an edge, then we're going to put this above the two vertices. Right? And so that's going to be how we say whether two vertices are connected or not. So say this is our graph, relatively simple graph, but generally we're dealing with infinite graphs, countable ones. It's going to transform into this. So here you have your A and you have your B, the elements that are bigger and greater than all the vertices. These three things are the vertices, and these are representing whether there are edges or not. So what I have to argue to you is from this, I can recover the original thing. So the first thing is I'm going to find this guy and this guy. So this is the only thing that's above a whole bunch of things here. And this is the only thing that's under all of those things. So I can recover those, right? Everything that this is above, this is below, and those are all incomparable. So I recover these. Then these are all the things that are in between those top and bottom things. So I can recover where the vertices are. And now I want to recover, if you tell me, is there an edge between here and here? Well, I look and I say, this element is less than both of those. So that means that there is an edge. This element is less than both of those. So that means there is an edge. This element is bigger than both of those. That means there's not an edge. So I can recover back the edge relation of the graph. So that's the idea, right? This is one of so I picked this example because of the list I had here. It's probably the easiest one. Some of these got a little more complicated because you're starting to involve some more algebra and things like that. All right, so and I want to talk about two special cases of trees and linear orders. So the ones we did before, they all have the same kind of strategy, which is we basically put the one structure inside the other structure, and we put things to say exactly how we did that. For trees and linear orders, we have to do something a little bit different. So I'm going to tell you how you do it, and then I'm going to tell you why it's a little bit different afterwards. So to start with, I want to talk with colored trees or labeled trees. So for us, a tree is going to have a distinguished root node, and then it's going to have a binary relation that says you're a child. I drew them going up, doesn't really matter. But then you should think there's also each of these vertices of the tree is going to be labeled with some label. We could think of those as integers. So given some structure A, I'm going to construct this labeled tree from it called T of A, or the tree of tuples. So it's going to be a labeled tree. It's going to consist of all the tuples from the structure ordered by extension. And then each tuple, right, is coming from the structure. It has some atomic type in the structure, and I'm going to label it by that. So for example, if the structure is elements A1, A2, A3, and so on, then this is what my tree is going to look like. So the root node is just the empty tuple. Its children are all the one tuples. The child of the one tuple is all the two tuples that extend it, and so on. So I'm taking all the finite tuples from the structure, and I'm arranging them in this tree of extensions. So at each height, you have tuples of that length. For convenience, it's often nice to just include infinitely many copies of things. So instead of including one copy of A1, sometimes nice to include infinitely many copies of A1. Right, and then we have the labels. So for example, if the original structure was a graph, well, there's nothing really to say about any individual elements. But for the tuples, they might have an edge between them or not. So I'm going to label each of these by, is there an edge between A1 and A2? Is there an edge between A1 and A3? So we'll have two labels, edge or not edge. For the three tuples, I have a whole bunch more options, right? Is there an edge between these two and not this one, and so on. So I'm going to have a whole bunch of labels and more labels as we go up the tree. So I think it's pretty clear that if the two original structures are isomorphic, then the trees that you build are isomorphic. But what about the other way around? How do you recover the structure from the tree? And the point here is that it's not like the original structure appears somewhere in the tree. You know, A1 appears here, but it also kind of appears here, and it kind of appears here, and it kind of appears throughout the tree in all sorts of different places. So it's a little more complicated to recover the original structure. So say we have two structures and we've built their trees, and the trees are isomorphic, and we've got an isomorphism between the two trees. Now I want to argue that the original structure is isomorphic, and it's going to use a back and forth argument. Essentially, this tree has enough information about the structure to recover a back and forth argument. So the picture here, I have the one structure by extensions, I have the other structure. And remember, I have some isomorphism between here and here. Now I want to build an isomorphism between the two structures. So I say, okay, let's pick the first thing from A, and I want to know where does it map to. So what I do is I look at the element A1 here in this tree, and I say, well, where does the isomorphism take it over here? It takes it to B3, so I say A1 is going to map to B3. Now I take, I have to do back and forth, so I take B1. So when I look at B1, I want to look at the two tuple, right? So far I've got B3, but I'm going to also have B1. And I can see where does it go? It goes over to here, to A1, A2, so I'm going to map A2 to B1. And I can keep doing this up the tree, and essentially what I'm going to do is I'm going to build a path through the one tree and a path through the other tree that are isomorphic via this isomorphism, and they're also total. So they include all the elements in the structures, and that recovers an isomorphism between the original two structures. And the labels here are important because the fact that this element maps to this element says that they have the same label. That means they have the same atomic type. The same things are true of them. Same thing for the two tuples. The same things are true of this guy as are true of that two tuple. Right? So when I'm building isomorphism, I really need it to be a partial isomorphism. And the labels are what's keeping that true as I build it. All right, so right, this shows that you get both ways. And so labeled trees are Borel complete. But we want to really show that trees are Borel complete. So you can just do this thing to code the labels into a tree. And this is like a little trick, but nothing really is happening here. So it's like a recursive way of doing it. So you have a labeled subtree T. I'm going to tell you how to define the unlabeled version. And it's going to involve how to do all the subtrees of itself as a recursive kind of argument. So say I have a tree T. The root node is labeled S, and it's got all these subtrees. So recursively, I can know how to transform all the subtrees. And now I want to transform this tree with its subtrees. So I'm going to define the transformation as follows. Basically, I'm going to put off like this extra little thing here. And remember, the root node here was labeled S. So that's really all I want to code in. So I'm going to put like this little split, and then S nodes here, and then another little split. And that's going to code that the label was S. Now, this split here is kind of saying that like this is the one that's coding things. This little split is saying that I'm stopping the coding. So you can recognize when you started to like where you put the S things and when you stop putting the S things. And then, right, I have all these subtrees here given by the T's. Well, I'm going to apply the same coding to them. So I'm going to take, this had some label. So I'm going to put a little thing off here. I'm going to put something going up here. All its subtrees kind of going along there. I'm going to run this along recursively. So basically, I'm just coding in these labels by having this little thing come off of every node that says what the label was that was going there. So again, right, essentially you can recover the tree and the labels from each other. And so this shows that trees are Borel complete. So we reduce structures to labeled trees, but then we reduce labeled trees to trees. And that shows that trees are Borel complete. For linear orders, essentially, you're going to take this tree and encode it into a linear order. So this one's a little more complicated. And maybe this one, for the sake of time, I'm just going to sort of give the general idea. Basically, the idea is that in the tree, so we're going to take the tree, and we're going to define for each subtree a linear order. And then we're going to shuffle those all together with little markers to say where they came from. So we're basically taking the tree and we're shuffling it in the linear order in a big way. So here, this is like a little element that we're shuffling. So we're going to put the label in. So we're going to put like a finite sequence of things to say what the label was. We're going to put these little delimiters Q to say, okay, here's where the label starts, here where the labels ends. And then we're going to encode all the subtree below the sigma over here. So this is like the encoding of sigma is you take the subtree below sigma and the label of sigma, and you put it in this little linear order. Now, what the linear order corresponding to the subtree is, that's going to be defined recursively. So that's going to involve the labels of the subtrees and all their subtrees and so on all the way through. And then when we define the linear order of a tree, what we're going to do is we're going to take for all of the children this little linear order, and we're going to shuffle them all together. And we don't want to just like put them in a line, because then there would be a first one and a second one and so on. So we're going to shuffle them sort of densely and co-densely. So this ends up being like quite a complicated linear order. It's actually quite hard to recover. It takes maybe like 3 jumps to recover the original structure from it. But maybe you could just believe that you can take this tree and like shuffle it into a linear order in some way. So these two had like a very different character from the previous example. So what is that, like, how do we get at that difference? So I said for graphs and for all these original examples, you can really find the structure inside of the graph. Like certain vertices of the graph, you can identify that represent elements. And there's certain aspects that allow you to recover the relations on the structure. But for the trees and linear orders, you can't really find the structure inside the tree or linear order in the same way. Right? It was this like back and forth relation that it somehow encoded it without really living inside of the tree or linear order. So the first kinds of structures where it's really the stronger kind of reduction, we're going to call that kind of behavior universality. But there's a bunch of different things you could formally mean by what this is. So here's like a little history of what people have meant by this over time. So maybe one of the first papers that really laid this out is this paper of Hirschfeld, Kuschanov, Shor, and Slinko. And so you shouldn't have to read the whole thing. Maybe just read the first sentence unless you're like a computable structure theorist. So the idea is that if you've got some property from this list of properties, that if you can build any structure at all with this property, then you could build a graph with that property. And you could build like a partial order with that property and so on. So all these properties are sort of like computability, structure theoretic properties. And the idea is that because you constructed some example of any structure, that structure really lives inside a group in a very strong way. Lives inside a graph in a very strong way. That graph is going to have the same properties. So this sort of transfer of the right kinds of properties over this Borel reduction is going to happen. Linear orders you can't add to this list. There are certain properties here that you can get in some structure, but you can't get in the linear order. Trees are maybe a little more complicated to talk about in this setting. So that's one way to say it, is that the stronger reduction gives you this like strong transfer of properties that's not just equivalence, but more things going on. Another way of differentiating it is to look at the inverse of the map. So on the one hand, you have this Borel reduction from one thing to another, and usually that's going to be functorial. So if you had some isomorphism between the original things, it'll transfer to an isomorphism of the things you constructed. But for these nice examples, there's also an inverse, right? We could find the original structure inside the graph. If you had an automorphism of the graph, it would induce an automorphism of the original structure just because it lives inside. So there's a functorial inverse to the Borel reduction as well. By inverse, there's some kind of category theoretic thing that you could say, but I won't get into that too much. But it's really saying that there's this like strong recovery of the coded structure from the structure that it's encoded into. So this is equivalent to a sort of type of bi-interpretation with the right kinds of infinitary formulas. I also won't get into that. But you can think an example of these bi-interpretations are really this, these facts that we looked for to recover the structure that induces a bi-interpretation. The two things have the same automorphism group. So the structure has the same automorphism group as the graph that you coded it into. And there's something even stronger that happens a lot, which is that the two processes are computable. So given the original thing, it's not just Borel to produce the graph, it's computable to produce the graph. and it's computable to recover the structure from the graph. So we're going to call this computably universal. And if something's computably universal, it implies this sort of transfer of results property, right? These are computable properties. So you need this computable universality to transfer these. And then there's also a version of bi-interpretation, which is a computable bi-interpretation that's the same thing. So you can prove that for trees that something like this doesn't happen. So there's a structure A, so that you produce the tree, like given this reduction, you produce the tree from it, where the structure doesn't have a computable copy, but the tree does. So in particular, right, if the tree is computable, you can't recover a copy of the structure because the structure has no computable copy. And moreover, this is true all the way up through the hyperarithmetic hierarchy. There's examples. And so what this is saying really is that there's no reasonable construction of the structure back from the tree. You might think, okay, well, the structure really lives as like a path through the tree, because if you take the structure and you think of it as longer and longer tuples, that gives you a path. But the problem is that there's all sorts of other paths through the tree which are not total. Right? There might be a path which misses a certain element. And how do you distinguish from a path that misses an element from a path that hits all the elements? Turns out that's very hard, and you can't actually do it. In particular, there's no interpretation of the original structure inside of the tree. And this was improved independently by Knight, Siskova, and Batev. And then I just want to talk about one last example, which is fields. So in the original paper, Friedman and Stanley, they showed that fields are Borel complete and universal. But in their argument, the recovery of the graph from the field is actually not computable. So you get transfers of like certain kinds of properties, right? This Borel completeness for the fields, but you can't transfer any computability theoretic properties between the two classes. And this was not known whether you could do this so that you could recover computably for a long time until 2017, where Russell Miller, together with Kunin, Schoutens, and Schlappentoch, showed that fields are computably universal. So you could code graphs into fields in a way that you could really recover the graph in a very nice computable way. So what is the idea? You've got some graph G, you want to reduce it to a field. So you're going to take the rationals in a pure transcendental extension. You're adding a bunch of new elements. And the idea is that these new elements are going to represent the vertices of the graph. And you want to distinguish, right? You want to do something to say, these really are the vertices. So you're going to add solutions to certain equations involving them. And this is where the tricky part comes, and why you need some number theorists is to tell you what the right equations are. So the idea, though, is that you can recover T by saying, I'm going to look for solutions of certain equations involving something. If I find it, I know it was one of these T's. And then for each pair of them, you want to say, is there an edge or not? So again, you take some equation involving those two, and you say, I'm going to put a solution to them if they're adjacent. And then there's some other equation, I'm going to put a solution to that equation if they're not adjacent. So you can look at those, and you can recover the adjacencies. Right? So this one, I'm not going to tell you how it works because it's involves like very particular kinds of equations. But it's really the same kind of structure as the ones I've shown you. All right, so that's it for today. So for tomorrow, we're going to continue. I'm going to talk a little bit about the isomorphism problem, which is something a little weaker. And I'm going to talk about some comparisons with the graph isomorphism problem in complexity theory. So this is with finite structures. There's some analogies and some things that look a little different. And then I'm going to talk about the case of torsion-free abelian groups, which is a sort of recent and very exciting thing within the last few years that these are universal. And I'm going to talk a little bit about how that works. All right, thank you.
Thank you, Matthew, for that. Now let's trade. And I get the wonderful job of running around and helping you ask your questions loudly. So who wants the first question? All the way to the back.
So with other notions of reducibility, like let's say, let's say a polynomial time reducibility, n continuous proofs. a lot of the time, the reductions have, produced structures that are atypical or even ridiculous. Okay, take the covalent theorem, SAT is NP complete. You take an NTM, computing in polynomial time, and you construct some Boolean formula that represents what this Turing machine is doing. And it's a ridiculous Boolean formula. It's huge, polynomially huge. It's still huge. And it's not like any formula you'd ever see in the wild. We wouldn't give an intro logic course where you tell students to make a truth table for this ridiculous formula. It's a strange formula. Or maybe another example, there's a result that chess is hard. Not 8x8 chess, but chess on an n-by-n board, generally. But the positions in the reduction are ridiculous. They have these gadgets in them. It's not like human players played this position. It's more like they conspired with each other and set up this position with gadgets in them. And it's designed to be hard to determine who's winning. So this is the case for Borel reducibility? Do you usually end up with structures that are atypical or even silly? I mean, like in the first example, you have the graphs, and they have these four cliques in them. I don't know, maybe that counts. Yeah, do you usually end up with strange looking structures when you're making these reductions? Does that question make sense?
Yeah.
It's an informal question. There's no formal sense of silliness here, but you end up with contrived or unusual looking structures when you try to prove reducibility.
Yeah, so I think that's probably true. So usually you have like the same kind of things showing up in all sorts of different places in the structure, which without other things showing up, which is maybe atypical. Yeah, so you should think really like like in complexity theory, right? It's saying that there's no like general classification of these things. And then you could start thinking, so in complexity theory, often you think of like, what's like my average case complexity or things like this. Here, that's maybe a little harder, but you can start thinking about like, what are the measure one structures? What do those look like? Or what the generic structures look like? And so there's some papers on that, like what does a generic group look like?
But in general, this is talking something more like worst case, right?
Yeah.
And you call it freedom to make the silliest looking structure you want, still counts. If you have a reduction.
Yeah, and maybe in some sense, because they're countable structures, you might have like somewhat less experience encountering like random ones than finite structures, right? For finite structures, it makes a lot more sense, like which ones you actually encounter because you're actually running programs on things. Countable structures, there's the ones that show up as invariants of actual things, right? Like which groups actually show up in the wild. And yeah, those ones like tend maybe to not look like these ones.
Thank you. I don't know if it's a quick question. Are there any like open problems of some class of structures that's not known to be Borel complete?
So the one I'm going to talk about tomorrow is one that until very recently was the big one.
Okay.
Uh,
All right.
Excellent teaser. Next question, we have time for a couple.
Thank you. Since generic was just brought up, right? Like, is there a kind of generic Borel reducibility that has been studied, and what do you know about it?
Yeah, I don't know if anyone's actually combined those two things to say sort of what happens on generic things. Yeah.
I have a practical question. Would it be possible for these slides to be available somewhere online for us to review before the next tutorial?
Sure. I can post them on my website, I guess.